He would deliver as a chaperone iron to heme synthesis and iron-sulfur cluster machinery. Obviously, we tried to dissect this pathway to try to see if we could, at which step we could show that this was the real function of the protein. So the first we used NMR. I come from a structural biological group, but I won't show you any NMR data, so be relaxed. And, but we could prove that Frataxin was binding iron, as someone already said. And it was basically in the region between the first helices and the first beta strand. There is a region negative charge where iron can adapt. Not as much as 6, but 2 iron could. So Frataxin is an iron chaperone. We want to basically try to verify this hypothesis. Why a chaperone? Well, iron is a lethal, but yet an essential element for life. It's essential because it's essential because we need for its redox properties, but it's lethal because a pH, a physiological pH, iron 2 doesn't exist, it's only present iron 3, and iron 3 precipitates immediately. It's a PS solubility, a KPS solubility very, very low. So you do need a machinery that, a protein that can deliver iron to the machinery, okay, of iron-sulfur cluster. And we actually looked at this hypothesis for both the mechanism, for both systems, the heme biosynthesis and the iron-sulfur cluster biosynthesis. But first of all, let me tell you, we decided to use, it's been shown that Frataxin is highly conserved as a sequence and as a structure, so as a fold. It's a highly conserved, so we do believe the Frataxin has the same function in the whole organism, okay? It might have an additional function, but the main function is the same. So we decided to use the homologue in bacteria because bacteria offers a very great advantage. All the genes for the machinery are in an operon, and so all decoded under the same promoter, so you could easily identify all the major players. And particularly, he highlighted, because I will talk later, these are the 2 major players of the iron-sulfur cluster machinery, biogenesis machinery. Is IscS, there is the desulfurase. Basically what it does, it takes a cysteine as substrate and producing alanine keeps the sulfur. And then basically ISU is the protein where the iron-sulfur cluster is synthesized de novo. And then basically you have other players that allow the de novo iron-sulfur cluster synthesized on ISU to transfer to any apoprotein to have the final product, the holoprotein. Now, we want to, as I will say you, as this beautiful painting of Caravaggio shows, we want to, as St. Thomas, to prove that that was the real function. And what we decided to use, 2 spectroscopy technique, the UV and the UV visible spectroscopy and the circular dichroic spectroscopy. These allow you to look at iron in general, iron complex. This one allow you to look specific at 2Fe2S formation because the CD is blind to 4Fe4S. And as you can see, the first things we did, very naively, we put the enzyme, IscS, the scaffolding, we put cysteine, iron, DTT, and we looked if we could follow in time the formation of iron-sulfur cluster on ICU. And as you did with both techniques, we can easily follow the kinetic. So then at that point we asked, what happened when you add Frataxin? Okay? As a chaperone, I would like highlighted here that we would expect or no interference at all, or an enhance of the activity of the IscS. That's what we would expect. But our surprise was very, we were very surprised to see that. As he reported, this is basically the kinetic, so the following in time of the iron-sulfur cluster formation on ICU without Frataxin, and this is when Frataxin is added. As you can see, the delay in the formation, the initial rate is very, very diminished respect when you don't add Frataxin. So Frataxin decreases the initial rate, so INS is an inhibitor. Okay? We were very surprised, and we didn't expect that for an iron chaperone. So at that point we want to go a little bit more further. Again, if you look at the reaction that it happens, again, this is very simplified, but you can basically divide the whole biogenesis of iron-sulfur cluster in 2 major steps. The first one in which basically IscS with iron presents and synthesizes the iron-sulfur cluster and ICU, and then when the second one went from ICU, the iron-sulfur cluster is transferred on the final acceptor. So we looked at the second step, okay, the one where you have ICU here already synthesized, and then you have the transfer. This is well known that you can do that. You can transfer on, and we use as a final acceptor ferrodoxin. And we followed the kinetic by CD. And as you can see, if you add or no, there's no difference when you add or no frataxin. So we could exclude that the frataxin was having an effect on the second part of the reaction. So then we looked at the first part of the reaction. Again with CD we followed, and very clearly you can see how when you don't have frataxin, and as soon as you add frataxin, the kinetics slow down even more with the CD. To be completely sure that was frataxin that was having the effect, what we did, we let the reaction go without frataxin, and then at 3 minutes we add frataxin that completely blocked the reaction. Okay? So we can now say that frataxin is playing a major role on the first step of the reaction. So frataxin need, more important, frataxin need IscS to show its function. Okay? No ICU, at least in the bacteria. So we were then at this point asking, is this the results of a direct interaction with IscS? Okay? And we used NMR again. We used a technique that's called chemical shift perturbation. If you want to know, I can explain you more. But we could see basically that there was an interaction, a direct interaction between IscS and ICU. And we were even more pleased and puzzled, not puzzled, but very happily surprised that basically the surface of interaction that frataxin shows to share with the IscS is the same where frataxin bind iron. So we were obviously very intrigued about this, so we decided to perform some mutants in that area to see what was at that point the effect of those mutants in this area, okay, where is the area where it binds iron and IscS. And you can see all the mutants here that are all in this area basically all revert. They all seems like you have not put frataxin at this point. And we use this mutant, the 776, as a wild type, as a control, because it's up here, it's in a region where it does not bind iron or IscS, and as you see it behaves as the wild type. Now, that is very intriguing, right? You have a frataxin that binds IscS and bind in the same area where iron binds. So, does iron have any function in this? So we try to do this assay. This is a bit complicated. Probably you have seen this in the paper, but this one probably is a little bit easier that we have just done now. So I did a Michaelis-Menten-like assay. We cannot really say that we are looking at Michaelis-Menten because it's very complicated what's happening. But what you can see is basically when you don't have frataxin, the initial rate of you have that kind of Michaelis-Menten. As soon as you put frataxin, you have that although a low iron concentration, the two curves seems the same. At the higher the iron concentration, the more difference you start finding between the two curves. So